Okay, the final topic after Chapter 2 is dimensional analysis, which is a great topic because you see this in high school, certainly in science classes and probably also in math classes as well. For instance, if you want to answer the question, how many seconds in a year? You go through a string of algebraic conversions like this: 60 seconds in a minute, 60 minutes per hour, 24 hours per day, 365 days per year. That gives me this many seconds per year. I've multiplied together the numbers, and that works because we think of the units being multiplied algebraically the same way that the numbers are multiplied. And minutes cancel, the hours cancel, the days cancel. All right, so if I wanted, for instance, the number of seconds in 10 years, I'd simply multiply this number by 10. Now, going beyond conversion from one unit of time to another unit of time, we can apply similar principles to equations in physics. For instance, the equation for a falling body is distance equals 16 times time squared. Now, this equation here for a falling body is only true if you measure distance in feet and time in seconds. If I measure distance in meters, this would not be true anymore. So I really need to consider that this 16 is not a pure number. This 16 has units attached to it. In fact, if I put in time in seconds and multiply by 16, I get out feet. So I need to consider that this 16 has units of feet per second squared. Okay. And here the time is measured in seconds squared. Now suppose I wanted to get the distance in meters. Well, I do a similar conversion that I did up here. I'm going to have to find something that gives me meters per feet. And it turns out that that's about 0.3. Then if I do the algebra on this, I'm going to get 16 times 0.3. That gives me 4.8. So the correct formula in the metric system is 4.8 times the time in seconds squared. Okay. Now, units refer to various physical quantities. For instance, feet measures length, grams measures mass, seconds measures time. Okay. So if we want to describe a certain quantity and we don't want to fix ourselves to a particular system of units, we can describe the type of physical dimensions that this quantity depends on. For instance, velocity. We measure velocity in feet per second or miles per hour. It's always length per time. So this description of velocity is independent of units. Velocity is always measured in length per time. On the other hand, if you're talking about density, that's mass per volume, it's always measured in units of mass divided by units of length cubed, because volume is always measured in units of length cubed. Okay. Now, for future convenience, instead of writing numerators and denominators, we'll simply use negative exponents. So L over T is equivalent to L to the first m to the 0 t to the minus 1. And m over L cubed is equal to L to the minus 3 m to the first t to the 0. I'm carrying the t because I might be interested in t in some other factor in my equation. Now, if I have a physical equation like d equals gt squared, actually this should be 1/2 g, but it's not a big deal. I can move everything over to the left-hand side. So for the equation to be consistent, I'd better have the same dimensional formula for every term in the equation. So d, the dimensional formula of d is L to the first m to the 0, t to the 0. I'd better have the same dimensional formula for gt squared. And in fact, you can work it out that it does have the same dimensional formula. An equation with this property is called dimensionlessly dimensionally homogeneous. This homogeneous is a little bit different from the homogeneous we've been talking about. Here, homogeneous means something like the same, or similar, or consistent. Okay, like homogenized milk. Homogenized milk is mixed in the same everywhere. Okay. Now, there are quantities that have dimensional formula where all the exponents are 0. For example, if you measure angle in radians, okay, I can measure the angle in radians by taking the radius and the arc and dividing the arc by the radius. Now, both of these are units of pure length, so I can divide them, and then I'll get something that has no units at all. This shows, by the way, that radians is the natural way to measure angle. The idea of degrees is multiplying by an arbitrary numerical factor, but radians is the natural way to measure angle, which is why mathematicians prefer it. Now, we want to use units for something more than bookkeeping. We want to use units to infer formulas for physical quantities. For example, suppose we have a pendulum. Now, you know what a pendulum is. It's something hanging from a roof or from a hook or something that goes back and forth, like a swing, playground swing. So how long does it take the pendulum to go from its position back to the same position? That's called the period. Now, expect that the pendulum is going to depend on other physical quantities involved in the system, like the length of the string, the force of gravity, the mass of the pendulum, so on, so on, so on. Question is, what formulas are possible? Well, you need to have a formula that's dimensionally consistent. Okay. So, for instance, if we list the possible physical quantities that could influence the period, well, there's a table on page 158. These are the quantities that we infer have some influence on the period of the pendulum, and their dimensional formulas. Now, in order to get something that gives me this dimensional formula, L to the 0, M to the 0, T to the 1, if I look down this list, the only quantity that has T in it is the acceleration of gravity, g. So I'd better have a factor of g in my equation. Okay. Now, the other thing you notice is that g also has an unwanted factor of L. So I'm going to have to do something to get rid of that factor of L. The way to do that, and there's only one way to do that, because the only other quantity that has L in it is the length of the string. So I'm going to have the period depend on g over L. Now, the problem is that g over L, if you work out the units, gives me L to the 0, M to the 0, T to the minus 2. Okay. If I want to get the period, which is T, I'm going to have to take g over L to the minus 1/2. Now, this doesn't tell me that the period is exactly equal to g over L to the minus 1/2. But it does tell me that the period, the formula for the period, is going to have to depend on this quantity in some essential way. Because this is the only way to get a physical quantity whose units agrees with the units of the period. So let's try to do this a little more systematically. All right, so what I've really done is I've covered this paragraph. As he mentioned, the period must be somehow a function of L over G, and in fact, you can go a little bit farther and say it must have some relation with the square root of G over L. So let's do this systematically. Okay. If we want an algebraic equation for a physical quantity, in terms of other physical quantities, we're going to have a sum of terms, and each term will have this form. We'll have physical quantities raised to powers. Okay? Each one of these physical quantities is going to have a dimensional formula. And in fact, from these physical quantities, I can arrange dimensionless quantities that have all powers 0, as this one did. L to the 0, m to the 0, t to the 0. So that's a dimensionless quantity. So my strategy is I'm going to gather all of my physical quantities. I'm going to try to get as many dimensionless quantities as I can. And then to get a formula for the quantity m1, to make sure that my dimensions work out, notice how it's been written here. M1 is some combination of the other physical quantities times some function of these dimensionless products. If I take this term over to the other side, I get another dimensionless quantity. So in the end, what I need to be able to do is I need to have an equation such that I can rearrange it to be an equation that involves only dimensionless quantities. All right, let's see how that works out for the pendulum's period. These are the quantities that we have. I want to find all possible dimensionless products. How do I do that? Well, I'm going to raise the period to some power, length to some power, mass to some power, acceleration to some power, arc to some power. And then what I want to do is I want to get dimensional units where the L's cancel, M's cancel, T's cancel. So all he's done here is taken these dimensional formulas, raised them to the corresponding powers, and set it equal to a dimensionless result. Okay? Now, you're going to get a total exponent for L, a total exponent for M, and a total exponent for P. So isn't that interesting? We have really an algebraic equation where we're multiplying and taking powers, but we end up with a system of linear equations. This is the power for L, this is the power for M, this is the power for T. And to have a dimensionless physical quantity, all of these linear equations must be satisfied. Okay, so we've converted the problem to a problem in linear algebra. Here we have a homogeneous system. We're experts on this. We can find a solution space, and it's parameterized in the following way. Okay. All right, now, so what we have here is two vectors span the set of dimensionless products. What does this vector represent? Well, the first component was the power of the period. So we have p to the 1. The second component was length. So that's L to the minus 1/2. Third component, don't remember what that was. Fourth component, that was g. That was g to the 1/2. Okay. So this is one of my dimensionless quantities, which corresponds to this. And this should look familiar. This is what we actually inferred already. This dimensionless quantity just depends on theta. Okay? So what this tells me right away is that if I want a formula for period, I'm going to have to be able to write that as P L to the minus 1/2 G to the 1/2, because that's a dimensionless quantity. That should be some function of the angle. Okay? This is in keeping with the statement up here. Right? Now I have a dimensionless quantity. I put these together to get the dimensionless quantity pi1, and that should be some function of the other dimensionless quantities. Okay? Okay? And he's just converted that to the form down here. He's just moved the L and the G to the other side. And it turns out that this function turns out to be a constant, turns out to be 2 pi. That's something you can't tell from dimensional analysis, but the remarkable thing is we've told so much about the solution without doing any experiments at all. Amazing. Okay, let's do the same thing with the period of the planets orbiting the sun. Let's see how far we can go just by consideration of the dimensions. Okay, so here are the possible physical quantities involved. The period, the separation between the sun and the planet, the mass of the planet, the mass of the sun, and the gravitational constant. All right, now, of course, way back in the time of Kepler, or the early people, they didn't know the units of the gravitational constant. That was something unknown. So they would not be able to infer this directly without information that the gravitational constant has these units. Now let's go through the same procedure now. We want to construct all possible dimensionless products from these quantities. And we set it up the same way. Take the first one, L0, M0, t to the first, raised to some power. Second one, raised to another power. And we want to end up with a dimensionless quantity. This gives me a system of linear equations for the exponents, which turns out to have this form. Okay. And it turns, so here we have two vectors which represent two dimensionless quantities. Here's the first dimensionless quantity, period times this junk here. Here's the second dimensionless quantity, which is the ratio of masses. Now, of course, these choices are not unique, but that turns out not to matter in the final analysis. Now, let me go ahead and do the same thing that I did before, that in order to get a relation for the period, I'm going to have to do pi 1, which is the dimensionless quantity involving period, should be equal to some function of pi 2. Okay. Now, if we rearrange that equation, we get a formula for period. Period is this junk times some function of the mass ratio. Okay. And here we have automatically that the period depends on the radius to the 3/2 power, which is Kepler's law. An amazing conclusion just from playing around with algebra. All right, here's another example. I'm not going to go through this because it's really the very same analysis. So you'll have a chance to do this same analysis for some other cases. And that's it.